I would like to present a framework for measurement-based quantum machine learning that I have developed together with Luis Calderon, Robert Rausendorf, and Dmitro Bondarenko. Because we have so much time for these talks, I thought I better start with a very basic introduction. And please ask questions along the way so that everything is clear. I would like to introduce the two concepts which are important for this talk. It's quantum machine learning and measurement-based quantum computing. In general, the characteristic property of machine learning algorithms is that they have the flexibility to improve their performance through experience. I think the easiest way to understand this is by way of an example. Here I look at supervised learning with neural networks. The basic processing units in neural networks are called artificial neurons. This is a diagrammatic representation of an artificial neuron. It takes a vector as an input, multiplies this vector with a vector of weights, shifts the result by a bias, and then applies an activation function. Typical activation functions are of this form, like the perceptron sigmoid rectifier, and this form is inspired by biological neurons. To obtain a neural network, we arrange neurons in layers and concatenate these layers with each other. In this way, the choice of the neuron and the geometry of the network determine the flexible algorithm. The algorithm remains flexible because the neurons are parameterized by weights and biases. And these are the parameters which we want to train. The goal now is to infer a map from a sample. For example, if we want to learn handwritten digit recognition, we may be given a sample of handwritten digits labeled by the numbers which they mean to represent. And what we want is an algorithm that can take any unseen handwritten digit and with high probability will output the correct label. This process, which optimizes the neuron parameter such that the network approximates the training data with respect to a cost function, is called training. And the typical cost function is the mean squared error between the correct labels provided with the data and the labels learned by the neural network. Oh, sorry. And as we have heard before already, training is considered successful only if the neural network generalizes well to unseen data. Now, in quantum machine learning, the difference is that this neural network becomes a quantum algorithm. The model becomes a quantum algorithm. And the training data consists now of pairs of quantum states. These quantum states can be mixed, they can be pure, they can encode classical data. A common cost function is based on the pure state fidelity, or let's say is the infidelity. It's 1 minus, and now if sigma and rho would be pure states, then this would be 1 minus average fidelity. Why are we interested in quantum machine learning? We hope that quantum machine learning will allow us to benefit from quantum speedups, but also that we will be able to solve problems from a larger complexity class using machine learning approaches, that we can use machine learning approaches to process quantum data directly, that it can help us to develop novel quantum and quantum-inspired algorithms, and that it allows us to exploit NISQ devices. This is because machine learning algorithms tend to be rather resilient towards noise in the hardware. Therefore, they are particularly well suited for NISQ devices. So this is what we would like to get from quantum machine learning. And here's what we have as of today. We have a zoo of proposed quantum machine learning algorithms that widely differ in the features that have survived quantization. We have proofs of quantum-enhanced expressivity for quantum kernels and quantum neural networks. For quantum neural networks, they are usually not advertised that much because they are pretty obvious. For quantum kernels, these proofs are more involved. There's quite some trainability skepticism because there are theorems showing that we may encounter barren plateaus in quantum machine learning, which means that the gradient becomes very small and it becomes very hard to train these models. And we have some proof of principle implementations. Notably, almost all proposals are based on the gate-based model. And this is where our approach differs. So let me introduce measurement-based quantum computing, and to be able to contrast it, we start with the gate-based quantum computing first. Here we have a qubit register, which we initialize. Then we apply gates from a universal gate set. For example, this can be the single qubit rotations around X and Z and the C0 gate. And then in the end, we measure in the computational basis. Measurement-based quantum computing works quite differently. We also start with an input state, but then we embed this input state into a graph state. This means that we have a graph, and for each node of this graph, we put a qubit in the plus eigenstate of the X operator. And for each edge of the graph, we apply a controlled Z operation. These graph states have a nice stabilizer property. If you put an X on an arbitrary node and Z on all the neighbors, we obtain an operator of which the graph state is a +1 eigenstate. Then the computation works by measuring all these qubits that are not the output qubits in this basis in the xy plane, which is parameterized by an angle. And these measurements are adaptive. This means that the sign here depends on the measurement outcomes that we have obtained before measuring a given qubit. This yields an output state modulo San Pauli corrections. Now, again, let us look at an example so that everyone has a chance who sees this for the first time to see how this works, and in particular, how the adaptation works. So we look here at the 3-qubit cluster chain. When we want to evaluate the effect of the first measurement, we can remove the 3rd qubit. We don't need it yet. And this is the equivalent circuit. So what does this circuit do? We have a controlled Z operation, psi plus, and then this rotation, which can be rewritten in this way. So the 2nd qubit can be in 0 when the 1st qubit is rotated psi. The 2nd qubit will be in 1 if the 1st qubit is Z rotated psi. Let us write this rotated psi as U plus V minus. Then the Z rotated psi becomes U minus plus V plus. Now recall that the Hadamard gate switches basis from plus minus to 0, 1 and back. Putting this together, we see the following. If the measurement outcome is minus 1 to the power of 0, so it's plus 1 and S1 is 0, then this means that we have projected the 1st qubit onto plus, right? So we obtain a U0 and a V1 from this line for the 2nd qubit. And this is rotated psi times Hadamard. And if instead we have measured S equal to 1, so a measurement outcome of -1, then we have projected onto minus here, and we have obtained a V0 plus U1, which is again Hadamard rotated psi, but with an X which switches the two basis states in the end. We can now proceed with measuring the 2nd qubit. Again, the 1st qubit doesn't matter, so we have to look only at 2 qubits, and we can apply exactly the same procedure as we have just done. But now let us immediately implement some measurement angle adaptation. We replace beta by -1 to the power of S1 beta. We write the expression that we obtained on the previous slide 2 times now, and we just bring this X to the other side. And what we obtain is a psi which has been rotated 2 times. When we bring this X to the other side of the rotation, it cancels this -1 to the power of S1. And in the end, we obtain a Pauli correction Z to the power S1, X to the power S2. Now, how did we know that this is the correct adaptation? We can see this by looking at the stabilizers of our cluster state. Let these projectors denote the two projectors corresponding to the two possible measurement outcomes. Let's assume that we have obtained the measurement outcome -1, but what we want for the computation is to implement the projection which corresponds to the measurement outcome +1. We can insert a stabilizer here because the cluster chain is an eigenstate, and then we can bring this projector to the other side. It turns into a plus projector, but we have this x2 and z3, which we have to remove to obtain what we wanted, which means we want to apply an x to the second qubit and a z to the third qubit if we measured -1 on the first qubit. Applying x to the second qubit is exactly the same as changing the sign in front of beta, and applying z to the third qubit is this z to the power s1, the Pauli correction on the output. I have gone into some details with this adaptation because the stabilizer argument can be generalized such that it yields a sufficient condition for deterministic processing in MBQC. And this sufficient condition is called flow. An open graph state has flow if there exists a flow function f, which maps non-output qubits to non-input qubits, and a partial order, which will be the temporal order, such that f always maps qubits onto their neighbors. F of I is measured after I, and all the neighbors of f of I, which are not I itself, are also measured after I. Again, an example. For the 3-qubit cluster chain, it's very simple. F corresponds to these arrows. It just goes along the cluster chain. And the temporal order will be measure this first, then this second, and then this one last. So why are we interested in measurement-based quantum computing, apart from the obvious reason that Robert is a co-author of this paper? Measurement-based quantum computing offers an alternative approach to quantum information theory. It is compatible with topological error correction. It gives us the possibility to parallelize all Clifford gates. It's also compatible with probabilistic entanglement gates, which is important for photonic implementations. And it allows for natural quantum classical interfacing, which can be interesting in algorithm design and also in quantum machine learning, because it already has some classical side processing, right? So we can play with this and modify it. There are also near-term devices, like, for example, Xanadu's MBQC device, which are under development. And this is a question which, the answer to which seemed very obvious to me until I have been asked it many times. So I thought I put it at the beginning of my talk. So why do we need quantum machine learning algorithm that we develop for MBQC? We could also take one of these proposals for the gate-based model and just translate, because both are universal quantum computing models. I think that algorithms that we obtain by translation are likely resource inefficient in MBQC. Now we could instead first translate and then compile them, but then I would expect that this will impair the algorithmic structure. So we cannot argue using this algorithmic structure. In machine learning, we usually have classes of algorithms and not one algorithm. So this can be tricky. On the other hand, if we design our algorithms for MBQC directly, we might be able to inspire novel approaches to quantum machine learning in general. But more importantly, we can use the MBQC resources efficiently. We can analyze our algorithms using the theoretical framework of MBQC, and we can exploit the features of MBQC. And honestly speaking, the first idea that brought me towards to this project was that local operations on a variable graph state, this already looks almost like a neural network. So my first question when I started this project was, isn't this already isn't MBQC naturally a quantum neural network already? it turned out that it is not quite as simple. We have to put some constraints, and this has thinking about these constraints has brought us to this definition of the multiple triangle ansatz, which is a framework for quantum neural networks in MBQC, and as far as we know, the first framework for quantum neural networks in MBQC. So not all graphs work. We wanted that we don't get unintended randomness. Therefore, we have chosen to look at graphs with flow. We wanted, of course, universality and a flexible structure. Therefore, we have decided to assemble our ansatz from universal building blocks. We wanted monotonicity of expressivity so that we know that if we grow our ansatz, we get more expressivity and don't destroy what we might have already gained. And we wanted some resource efficiency, which for us meant we wanted small building blocks so that one can start implementing them on on near-term devices. And this is the structure we came up with. This is, of course, an example. And let me walk you through the blocks and how it is assembled. So we see here a concatenation of layers. Each is 5 qubit deep. 1, 2, 3, 4, 5. This is one layer. And the next layer starts with an overlap because the output of one layer is the input of the next one. A layer characterized by n and I has n wires, like width n, connected by triangles with tips anchored at wire I, for example, here at wire 0. The triangles are always such that the tip is at qubit I1, here, 0, 1 in the layer, and the base is symmetrically around it. So like J0, J1, J2. The width n and intra-layer connectivities, I mean, which triangles do you put and which triangles do you not, do you remove, they're free to choose. You can also freely choose the interlayer connectivity, which means you can have different widths of the layers, or you can also have 2 layers of the same width but decide to displace them with respect to each other, something like this. And the variational parameters in MBQC quantum machine learning are, of course, the measurement angles. So let us see which properties we could establish. The MuTA graphs have flow. I show it here for a simple block, but this is true for any geometry. They can implement arbitrary 1 qubit gates. Here, what is written down here is the Euler decomposition of a single qubit gate. And on top is the implementation via a one-wired MuTA. They can also implement a 2 qubit entangling gate, the Ising X gate, which is entangling for a proper parameter choice of phi. And this establishes universality of the ansatz. We also almost have monotonicity of expressivity. And you will see why almost. So we can easily add additional layers because we can show that they implement the identity if measured in X. Here I show only weak monotonicity because one can easily design naive examples where you don't change the expressivity. Like, for example, taking single wires and making them longer and longer will still implement single qubit unitaries. If we add an additional wire, we apply a 1 qubit gate to an additional input qubit. But of course, the expressivity on the input qubits that have been there before we added the additional wire doesn't change. And if we add additional triangles, then, for example, such a MuTA will implement the same gate as such a MuTA with a proper choice of betas, which will depend on the alphas here. Now, as you might notice, I have added qubits here. Honestly speaking, if I would write this paper again, I would make the ansatz 1 qubit longer. Right now, if we want to stick with the smallest possible building block, if we want to add triangles to preserve the expressivity, we have to add an additional MuTA layer after the added triangles. And this is because here, if we would not add this additional qubit, we would have only 2 angles. But for the order decomposition, we need 3 angles. So before we added the triangle, obviously, we could implement any single qubit unitary here. And now, to implement any single qubit unitary, we need 1 more qubit. Yeah. To prove this, we actually did not use directly MBQC techniques. We translated it into a gate-based circuit. And this is what you see here. So this is the unitary, which is implemented by a fully connected MuTA layer. And if the MuTA layer is not fully connected, then some of the Ising gates here have to be replaced by single qubit rotations. Yeah. So it is very important to note that these Ising gates correspond to the measurement angles at the bottom center of triangles. Using this same translation into the gate-based model, we could show another interesting property, which we call tunable entanglement, which is exactly based on this observation that we have only one type of entangling gates, these Ising XX gates, and that they are parameterized by this angle. So if we start with such a product state here, and this angle here is chosen to be 0 or pi, then the result is separable. Yeah, so we have not implemented any entangling gate between this wire and any other wires. On the other hand, if we choose phi different from 0 and pi, then there exist psi 1 and psi 2 such that the result will be entangled. Right? So this means that if we know that we don't want to entangle some inputs in our ansatz already, we can just remove the triangles. But if we don't know, the algorithm has an efficient way to learn whether entanglement should be implemented between these inputs or not. So in addition to this, we have some more properties. I have already talked a little bit about the versatile algorithm design, which is very important for machine learning. We can specify a MuTA graph, and what I have not talked about yet, we can also restrict some of the measurement angles if we want to engineer a bias. We also have very good scalability in the sense that fully connected layers have no more than linear in width and depth variational parameters. This is very nice because it means that we don't have to make the decision of how we want to sparsely interconnect layers to make this thing trainable. And MuTA graphs are two-colorable, which is a nice feature if we want to use purification protocols on the graph states. Now, with all machine learning algorithms, I think it is very important to show that they can be trained, because this is obviously not part of our properties of the ansatz. And therefore, we have looked at some numerical examples. For example, we wanted to show that we can learn a universal gate set. We have chosen an ansatz, a very simple MuTA layer. Our data was provided in the form of high random states as input and u times high random states as labels. The cost function was 1 minus average fidelity. We used the Adam gradient descent. And we have learned random local unitaries and the Ising XX gate. And you see it converges quickly. Then we have added Brownian or depolarizing noise, which means that we have assumed that the data is corrupted. To each label, we have applied this Brownian process. So for we have applied random Hamiltonians with normally distributed elements for small amounts of time in sequence. And as you see here, of course, with increasing noise strength, the fidelity of the training data decreases. However, it doesn't do it very rapidly. So there's this nice behavior, and also it performs better on the noiseless test data. This means that while the data on which it is trained is corrupted, it still predicts the correct, uncorrupted desired output on the test data to a quite high percentage. Then I think a very important benchmarking experiment for quantum machine learning algorithms is the classification of quantum states. And in the most general case, classifying quantum states means performing a POVM and then adding classical post-processing, because quantum state tomography is a POVM, right? So we can describe everything by this ansatz. And the POVM can be again described by PVM, by ordinary projective measurement on a larger system, as we know from the Naimark dilation theorem. The example we have chosen here is a classification by the quantum Fisher information. Therefore, I would like to say some words about quantum metrology and why the quantum Fisher information is important. If we want to estimate a parameter theta from many measurements of a state psi, which depends on this parameter theta, then the variance of the estimator is limited by the Kramer-Rao bound. And this Kramer-Rao bound depends on the quantum Fisher information. So the larger the quantum Fisher information, the better our estimation can work. And for separable probe states, the quantum Fisher information is bounded by the standard quantum limit, while for entangled probe states, it is bounded by the larger Heisenberg limit. In our specific example, we have two qubits. The phase is imprinted in this way by a collective Hamiltonian. And this means that the quantum Fisher information is 4 times the variance of this Hamiltonian in the initial state psi, and the standard quantum limit equals 2. We wanted to formulate an ansatz which uses the information that we have a collective Hamiltonian and is sufficiently powerful such that we know that the correct answer can be formulated within this ansatz. So what we use here is such a MuTA with equal angles on the 2 wires and without triangles. This is because our Hamiltonian is collective, and applying such a MuTA to the input state transforms the input state in the form U tensor U with single qubit unitaries and gives us access to the probability distribution of measurement outcomes we measure here and that. The variance that we want to estimate here, the quantum Fisher information, is a second order polynomial of 2 of the probabilities. And that's how we formulate the classical ansatz, the classical post-processing. And the training data is chosen from these 2 sets. We classify states with a label 0 if the quantum Fisher information is below the standard quantum limit, and with a label 1 if it is above the standard quantum limit. And we wanted to use a training set that is not random or something like this, because the practical application we have in mind that you might have a classifier that you can easily check on some states which are reasonably simple to prepare, but not in the entire Hilbert space. And of course, we have carefully chosen the training data in a way that we cover a wide range of values of Fisher information and also of probabilities of the measurement outcomes. The loss function that we use is this one. This is a typical loss function in classification tasks. It increases the error if we misclassify by more, and it contains this epsilon to prevent that everything is put exactly at the separating line, in which case we would have no error at all. And on high random test states, so in the generalized case, we find a classification accuracy of 93%. As a final example, we wanted also to classify classical data, and we used a kernel method to do this. Now, support vector machines have been invented for linear classification. The idea is that you have data in the following form. You have some vectors. Some of them are classified by +1, some by -1, and you want to find a separating hyperplane, which is characterized by this orthogonal vector W. You want to optimize W and B in such a way that you maximize the margin between the separating hyperplane and your data, and of course you classify the data correctly such that data classified by +1 is on one side of your hyperplane and by -1 on the other side. And then inference for new data points works, of course, by looking at the site at which you are with respect to the hyperplane. This idea has been generalized to nonlinear classification by embedding your data into a higher dimension before applying a linear classification. In the Lagrangian dual of this optimization task, training and inference become functions of scalar products. So to realize the embedding, you simply replace these called scalar products with the kernel function. In quantum kernels, the typical way to define such a kernel function is like that. This is maybe not the best way because it actually does not all properties of classical kernels survive quantization if that's what you do, but it is a very popular way to do it like this. And we have used the MuTA ansatz to define the states phi of x prime, right? So the MuTA implements a unitary. If we apply to a reference state, which in our case is just 0, 0, we obtain some embedding. And these are the angles that we have used for our MuTA state to embed the classical information into these quantum states. And here are the results we get for some artificial data sets. We see that we can do nonlinear SVM, but not if it's very complicated. So the moon shapes didn't work out with this simple ansatz. However, this is comparable to state-of-the-art quantum SVM for gate-based models. So finally, we started to think again about how this can be implemented on hardware. And for example, Xanadu has recently realized their first qubit using Gottesman-Kitaev-Preskill encoding. In the Gottesman-Kitaev-Preskill encoding, the two qubit states 0 and 1 are realized by two displaced comps of quadrature eigenstates, approximately, of course. This is a very convenient encoding because it allows for the deterministic implementation of controlled Z gates. Measuring X and Y can be realized by homodyne detection, and it allows also for continuous variable error correction. However, to reach universality in MBQC, it is not sufficient to measure in X and Y only, because this would correspond to applying only Clifford gates. So to solve this problem, we can inject a magic state in the following way. We can replace a plus state by this A state, and then measurements of X become measurements of X plus Y. I mean, a measurement of X on this new state is the same as a measurement of X plus Y on a plus state. However, if you want to design quantum machine learning algorithms for this situation, for this hardware, then we have to optimize over this discrete set of angles. This is typically very complicated, so what we develop for this is a simple heuristic. We initialize our MuTA with random measurement angles, and then we optimize over temporal slices. First one temporal slice at a time. If this doesn't work sufficiently well, 2 temporal slices at a time, and so on, until we either succeed or restart. And what we see here in this diagram is that on a simple task of learning this gate, we're at least much better than the worst case random search. And with this, I would like to come to the end of my talk. We have proposed the first measurement-based quantum neural network, which we call MuTA. The MuTA ansatz exhibits several favorable properties, which we have proven, including determinism, universality, tunable entanglement, and monotonicity of expressivity. We have shown via simulation that it is applicable to various tasks, and we also have discussed how we can incorporate hardware constraints. However, I would say that this work opens more questions than it answers. For example, there has been a paper from a different group where they leverage randomness by doing probabilistic adaptivity. This could be combined with the MuTA ansatz, because in other parameters, our ansatz is much more flexible than there. It would be interesting to see how this can be used for learning channels or doing generative modeling. Then I have already mentioned that MBQC allows for natural interfacing with classical processing, and would be interesting to explore this in more detail, doing hybrid quantum classical algorithms, which are interfaced at mid-circuit measurements, because it is known that this can make algorithms very much more resource efficient. And to do this, we want to develop recurrent quantum neural networks. Then it is also not entirely clear to us how to do measurement-based quantum machine learning with topological error correction. So whether it is a good idea to do it without and then add the topological error correction, or whether we should do the machine learning immediately in the error-corrected setting. Of course, the dream of most people doing quantum machine learning is to have provable quantum advantage, including training. And this is very far from being understood, and it's a very interesting question. And another interesting question would be, so it is very simple for neural networks to show that the expressivity of quantum neural networks, if you look at like the infinitely large neural network, is better than the expressivity of classical neural networks in this at this infinite sized networks. But what about finitely sized networks? So if I pick a geometry with a given number of nodes, for example, can I show that the quantum neural network with the same geometry and the same number of nodes will have a strictly great expressivity? This is an interesting question which we think might be addressable for MuTA, because we can find a one-to-one mapping between classical geometries and the geometries of our quantum neural network. With this, I'm at the end of my talk. Thank you for your attention, and I'm looking forward to your questions.